Okay, here we go. So the first question just said, generally, what's the temperature doing for these 15 minutes? So we start out with what kind of rate of change? Negative rate of change means temperature is for about 4 minutes, or 3.8 minutes, whatever, something like that, okay? Temperature is decreasing for the first about 4 minutes, and then until when is it increasing? 13, 13.1, 13.2, okay? The temperature is not going down after what? What is that? What did I do? What did I just do? Okay. Okay, the temperature is not going down, right? Starting at 8 or 9 minutes there. Starting here, the temperature's not going down. Why not? Positive rate of change means temperature's going up. It's just going up at a slower and slower rate. It's going up, but it's going up at a decreasing rate. Okay? And then after 13.2 minutes, then the temperature decreases again. So decreases, so the general answer, number one, decreases, increases, decreases. That's what the temperature does for these 15 minutes. Okay, so let's skip to number 3, which said, when is the temperature the lowest then? In these 15 minutes, when is the temperature the lowest? Here. Why? Because it starts at, 40, and it goes down this whole time. And then what about the amount that it goes up compared to the amount that it went down? Thinking about our constant rates and finding amounts of accumulation, what could we say, could we pretty easily conclude about how much it goes up compared to how much it went down? A lot more, right? A lot more up than down in this first 4 minutes. Okay? So therefore, is the temperature higher or lower than the initial temperature right at this time? Higher. Higher than the initial. Okay? Meaning that then the overall lowest is probably here. Now, if we had a couple more minutes, now we'd have a choice to make, right? If a couple more minutes went by and the rate keeps dropping like that, negative, then we have another choice. But just in these 15 minutes, pretty obvious that the lowest is here. Okay, so and then when's the highest? So when is the highest temperature in these 15 minutes? Round 13. Round 13. It went down a little bit, but it went up a whole lot more, so now it's higher than when it started. Okay? All right, so what about the first time that it returns to its starting temperature? So remember, with a changing rate function, we can't really talk about accumulated amounts or amounts. So here's one way of thinking about this. Let's think about it in terms of having some approximating constant rates. And so you're thinking about, okay, it goes a certain amount down, it goes a certain amount down, it goes a certain amount down, that we could calculate now, right? We could calculate these. And then it goes a certain amount up, and then it goes a certain amount up, and then it goes a certain amount up, and it keeps going up. So would you just thinking about calculating changes by constant rate times a change in x, where along the way would you just kind of estimate that it returns to the initial temperature? If you said 7 to 8-ish, that's pretty good, okay? Why? Because it's going to go down, and then it's going back up. So around where would it return? Somewhere 7-ish, 8-ish, something like that. Obviously, it's gone up by 10, 11, 12 minutes. It's gone up a lot more if you think about the dy's that we would get. Okay, please don't start talking. Okay, if you think about the dy's that we would get for each of those constant rates, the more of those positive ones you have, the more that you're going up and surpassing the initial temperature. So where does it balance out? It's kind of we're looking. Where does the total negative accumulation balance out with the total positive accumulation? Somewhere around 7 or 8. Okay. Okay, so we've got these. The next thing I ask you to do is the definition of The exact accumulation of changes. So before we do that, we say, where does that come from? Where do we get it? How do we get exact accumulation of changes in temperature? So that we talked about that on Tuesday. Really important idea. We've got the approximate rate of change function. How do we get to the point where we say, okay, we want the exact accumulation of changes in temperature? What's the bridge to that? What's that? No, not quite. So we've got yes and no. So yes, that's not incorrect. But thinking about getting it from an approximate rate function. So if we're starting with we've got our approximate rate function. What do we need next? Yes, sir.
The change is really, really small.
Okay. So does that? All right. There's the change is really, really small. Does that give me exact accumulation? There's no accumulation right now. All we've got is rate of change. Do you see? There's no accumulation. So what do we need next? Yeah, we need that big long function that we worked about a week and a half on, that hard function, right? So we need approximate accumulation first, right? So from approximate rate, we can build approximate accumulation. And now, to get exact accumulation, what do we do? If we make delta x smaller, our approximate rate function does a better job of pretending to be the actual rate function. And therefore, the approximate accumulation function is better. So here is a delta x of 0.025. And what's happening? That's a really small delta x, 0.025 minutes. And so what's happening? GC is having to work really hard to accumulate all those tiny little changes. Take 15 divided by 0.025. How many changes are there in these 15 minutes? Take 15 divided by... We're talking about 600 moments. Breaking up those 15 minutes into 600 moments. And so that's a lot of work, right? That's a lot of calculating those bits of accumulation to come up with the accumulation graph. That's why it's taking GC some time to do that. Okay, and if I turn off the exact rate, what do you see over there? It looks just like the exact rate, right? But if I zoom in again, what is it? Still approximate rate. But the moments are so small that if you just blur your eyes a little bit, you just say, oh, that's pretty much the exact rate function, right? The moments are so small that all those constant rates are doing a really, really good job of pretending to be the actual rate function. And so we have this idea of the moments are small enough so we can't tell the difference between approximate and exact. All right, so we keep making the moments smaller and smaller until they're small enough, right? There's no distinction. There's no important distinction, I should say, or significant difference between approximate and the exact rate function, and therefore no distinction between worth noting, right? So the distinction now is so small between the approximate accumulation and the actual accumulation that we call it even. We call it even. Okay? All right, so here is the exact accumulation function. This is the one you had to write on your quiz. We'll show it in a second. But here it is, and so if I show, okay, so if I turn on the exact accumulation, how is it going to compare to the pink one? It should be right on top of it, right? Because our delta x is so small. So I made it black. Okay, so I made the exact accumulation black, and it's just covering up, basically covering up the purple one, which was the approximate accumulation with super small moments. Super small moments. Okay, so what is that expression? So what is that expression? So here was approximate accumulation, right? Here's approximate accumulation. And so then your exact accumulation is the integral expression. Okay? Big important point. These two things are the exact same function except for one thing. What's the one difference between these two functions? When we express that big long formula that we worked on, and now we express this integral expression, what is this? This is really just one primary difference between those two. Is that what you're saying? Is that what you're saying? Yeah, go ahead.
I was just going to say that there's no appreciable difference between the moment and the change in t.
Moments in the change.
So the delta t, and dt are essentially the same.
The key thing is these are the same. This is this for super small moments, not supper. So here I've made delta x 0.025. We can make it smaller if we want, okay? That's is. But this integral expression is the exact same thing as our approximate accumulation function with super small intervals, or super small moments. Super small moments. Okay? And we talked about the similarities. German S. German S stands for sum, just like sigma standard for summing up, little changes, right? What is 0? 0 is our value of A. This is where we're accumulating to. It's the same in both cases, right? The independent variable is where we stop accumulating, or where the current value of x is. So from 0 to x. And then we saw the very important, inside this, what is inside, or next to that integral sign, I'll put it in red. We should recognize that as a really important foundational expression right there. Let's see. Where is? Junsi, Zhao. Yeah, tell me about what I put in the red box. What does that mean? Why is it important? So what I put in the red box is the exact accumulation function. Where's Mei Chen? Do you agree with that? He said what I put in the red box is the exact accumulation function. Agree? Where's Michael Dagger? What do you think, Michael? What I put in the red box. Just the r sub t dt. Okay, don't start talking. Nice enough. The completed and current intervals. Okay, you guys, come on. Kyla Richardson. Where's Kyla? Yeah. Oh, this hurts my heart. R sub t dt. That's a product of two things. And the most important product we've talked about in the last month. Okay, and what does it mean? How about Kenneth Kowalski? Kenneth. Right, and what does that give you? Like MDX, good. Like MDX, and is that, you said that's not accumulation. Is that not accumulation? That's a little bit of accumulation. That's dy. That's a little change in our temperature. Right? And that's what this whole thing up here is based on, right? This is what this whole function up here is. The sum of r times delta x plus one more, r times change in x. Remember that the approximate accumulation function just boils down to adding up changes in y as m change in x plus m change in x. All the completed intervals, that's the left side, plus one more m dx for the current interval. And so it's the same thing. The integral means sum up a bunch of m dx's. It's just now that the moment is so small that we don't distinguish between a current interval and completed intervals. X is just increasing through these super small intervals and racking up the accumulation little by little. As x is moving, as x is increasing, it's just racking up dy's, dy, and we're just adding them up as we go. And that's what that means, summing up a bunch of dy's continuously for super small intervals. So I hope lots of you who I didn't call on had that in your mind, but got to get this. That's like the key idea of all this. So when we make the moment really small, we can use the integral notation, and it's small enough so that we're talking about exact accumulation. Okay. So where do I want to go next? Where were we? Okay, so we said, okay, so then the next thing is, we've got the exact accumulation function. What about this function t? So this is a sub t, which what I want you to do actually before we go on. Can you express the exact meaning of that right there? Okay, so in words. Can you express, and we talked about this last time, in words, what is that right there? So take a moment to talk to the person next to you. Express that in meaning.
Mark, we're ready to go ahead and pass back the quizzes if you want us to.
What do you think?
Or do you want to wait till the end of class?
Yeah, it might be
End of
distracting.
class?
I think so. Did you say this? The accumulation of small changes in temperature starting at 3 p.m. until X minutes after 3 p.m. Okay? Hopefully, so I would guess some of you said parts of that, or most of it, hopefully. That's what the integral expression means. The accumulation of small changes in temperature starting at 3 p.m. until X minutes after 3 p.m. Or starting at x equals 0 until x, if you can say that too. Starting at x equals 0, which is 3 p.m., until x. Okay, so how is that different from the function t? So then you had to write the function, what did you have to do? You had to write the function t. So we've got this a sub t function. So that's giving the accumulation of small changes in temperature. The capital T function was the temperature function. So how do we get the temperature function from the accumulation function? It's just not going to start at 0 anymore, right? It's going to start at 40, so all we need to do is add 40. There it is. So you're going to start at 40, and now you're going to start accumulating changes in temperature with the integral starting from 40 rather than starting from 0. Okay? And that gives you the temperature at any time x. This.
I have a question for the starting point of the sum.
Yeah.
Does it matter if it's A or 0?
Well, so I wrote A here, so I should have wrote 0. So I have A defined as 0 earlier in GC. It would be 0. Yes, for this one, it's 0 because we started at time 3 o'clock was time equals 0. So I wrote A here, could have wrote 0. For this particular example, we're starting accumulating at x equals 0, so that's our value of A. Yeah. Do you have a question too?
Yeah, the same thing. So like for the quiz is 301 to 305. So could you have done like 1 to 5?
Yeah, we're gonna do that. We're getting there.
Okay.
We're getting there. Okay, so now if I turn on the temperature function, let's make it, I don't know, I'll make it black also. Okay, where is it? So nothing appeared. Why not? Where is it? Where does it start? It starts at 40. There it is. So now we're talking about temperature, which starts at 40, but then follows the exact same pattern of accumulation, right? We add the integral. You're going to accumulate changes from 40 instead of from 0. So now there's your temperature function. And that's your sketch. So this is the sketch that you made. And so it doesn't have to be perfect, but as long as you show it going down, returning to 40, going back up, and then heading down again at the end. That's the general idea of the temperature function that you sketched. Okay? Okay, so we want to express the temperature. So we got this temperature function. How can we express the temperature in 2 ways at, what time did they say? At 3:10. So using function notation, how can I express the temperature in the fridge at 3:10? Good, T of 10. And since my function is defined, what just happened? GC just told me what T of 10 is. So at 10 minutes, the temperature now is 42.8 degrees Fahrenheit. Okay, so I want to point something out. All the functions you've worked with in your past are what's called closed functions, meaning you could take your calculator and put 10 into some formula and would crank out that answer, the value of the dependent variable. This is not like that. This integral expression is what we call an open expression. And you saw how long it took for the GC to do it, right? So it's a lot of work. So it's reflecting the process of accumulating all those bits, okay? It's reflecting the process of accumulating all those bits. So there's not, in that, the way that function is defined, there's no formula that we can put in 10 and it'll give us 42. And we can put in 12 and it'll give us the corresponding temperature. We can put in 5. This is the idea of an open expression. It means it's representing process. And we need technology to give us a result. We don't have a formula yet. Okay, we don't have a formula for that integral expression. But GC knows what it means and does a numerical method just the way we're talking about, bit by bit. It's going to sum up all these bits according to that rate function and give us a really close value. Okay, so at this point, with these accumulation and amount functions expressed in integral form, we need GC to give us, if we want values of the dependent variable, we need GC to do that for us. That's not a formula that you plug 10 into and punch some numbers on your calculator fast and get a result. Okay? So for these accumulation and amount functions, at this point, if we want to get a correspondence points, if we want correspondence points of integral expressions, we need GC. We need GC. Don't have a quick formula. Okay, so that's T10. How else could we express that same thing, the temperature at 10 minutes, using the integral? So Control-Shift-I. So what integral would I put in to get that same temperature? From 0 to 10 of my R Try that again. Okay, so my integral from 0 to 10 of r t. Okay, so this little t that we use, it can be anything. So this time I'll use v, okay? So it can be anything. It's just a placeholder. All right? So it could be v, it could be u, it could be t, and we're going to talk about that later today. So how come it's not 42.8167? What is 2.81667? So what would that mean? So where does that number come from? It's just the accumulated changes in temperature, right? So if we want the temperature, just like in the t function, we got to add 40. And that's the two expressions that would tell us what the temperature is at 10 minutes. Okay? All right, so now, the change in temperature from 301 to 305. So using function notation, I want the change in temperature using function notation from 301 to 305. So it'd be T of 5. So this is the change in temperature. So this is back to our function, using function notation to represent changes. What about, can I just do T of 4? Can I just do T of 4?
No.
What does T of 4 mean? It does not mean the change from 1 to 5. T of 4 means the temperature at 304. If you do T of 4, you're talking about the temperature at 304, not the change from 301 to 305. Okay? So how can I express this with an integral expression? So I could do, that's T of 5 as an integral, right? And then I could do what from there? Minus T of 1. I get the same change in temperature? Okay. So yes, you can just use the rule, that rule for T of 5, and subtract the rule from T of 1, and that would be an integral expression getting your change in temperature from 1 to 5. But let's think about what we're asking. We're asking, we want the accumulated changes in temperature starting at 301 and ending at 305. We can do this a lot easier. We can do this a lot easier. How can we, if we just think about the meaning of what we're setting up, I want the accumulation of changes in temperature starting at 301 and ending at 305. It just takes one integral. I want to accumulate starting from when? 1. 301. So I can make, it's kind of like changing A. Now for this, if I want the changes from 301 to 305, it's like A equals 1. Until 5. And I'm just going to copy and paste here. And lo and behold, what do we get? Okay, so that the yellow blocks expression is perfectly fine. You're taking the expression for T of 5, literally, and subtracting the expression for T of 1 to get the change. But if we think, again, if we think about what's being asked, it's exactly what an integral calculates. The accumulated changes in temperature starting at a certain point and ending at another point. So it would just be, from 301 to 305, would be the integral from 1 to 5. A really crucial point here. Does it make sense? So that's what you're talking about, right? Yeah. Okay, cool. So the last one, so then, do I need to be looking at the temperature function? Where is the temperature function? Oh, it's gone. Where are you? Did I turn it off? I turned it on. Oh, there it is. Okay. All right. So, so when I'm talking about like the change in the accumulated changes in temperature from a certain point to a certain point, I can really, does this initial temperature matter? So let's talk about, so showing on the graph. So T of 1 is like this. So here's 1. So this is my temperature. So here is, right there is T of 1. Okay, and then here's 5. So T of 5 is somewhere over here. And so how is that change in temperature expressed on the graph? So what on this graph is showing that change in temperature from 1 to 5? Okay, so it's this change right here. Do you see that? From here to here is showing that change of negative 0.73, 157, etc. So that's that change. Starting at 1 to 5 is that change. I don't need the temperature function to talk about that change in temperature. I could also use the accumulation function, right? If I go down to, watch, I'll just keep that on the screen, watch. And I'm going to go back down to the accumulation function, which starts at 0. I don't know where it would go this way, but we'll just guess. Oh, right, it's got to be points on the curve. There we go. All right. Oh, got it. Okay. So look. So this is now the accumulation function. It's the exact same. So T of 1 is now this accumulated amount of changes. And then T of 5, that accumulated amount of changes. So the difference of, this is now the difference of what? A sub T of 1 and A sub T of 5 is the same. Because we're just finding a change in accumulated amount. So it doesn't matter if I use the temperature function or the exact accumulation function. It's going to be the same change, So T of 5. And so let's show it again. So I come here and I'll do A sub T of 5 minus look, same thing. Because it's just based on the changes, starting at 1, ending at 5. Doesn't matter if it's the temperature function or the accumulation function. I got the same change again. Okay, does that make sense? Okay, so the largest change. From what's the starting time and the ending time that gives me the largest change in temperature? Largest increase in temperature. Well, that's like, so from about 3.8, I'm guessing, to 13.2. This is the largest increase in temperature. Starting here to there. And what's true about the rate graph? What's going on with the rate graph with that change in time? The largest positive interval, right? The rate is positive for the most time. So we get the largest increase in temperature, and so we want to express this the easiest way possible using an integral. Can you express that change in temperature the easiest way possible using an integral? I'm calling it 3.8 to start and 13.2 minutes to finish. So as an integral, what integral could I set up to get this largest change in temperature? Where's Manuel? Perez. 2 days in a row. Manuel. So what integral would give me that largest change in temperature? So use the ones that I did.
From 3.8 to 13.
Right, so we can start from 3.8 to 13.2 of So do I need the temperature function to do this largest change in temperature? No, I could just use the accumulation function. You see, I can just use the accumulation function and make it from starting at 3.8 to 3.2. And what are the accumulated changes? It has nothing to do with the 40. The change in temperature from 3.8 to 13.2 minutes has nothing to do with it 40. It would have been the same if we started at 15 degrees or -5 degrees, that change in temperature, if that's the rate function. It only depends on the rate function, doesn't depend on the starting temperature. Now, if you wrote it in terms of the temperature function, that's okay. That's okay. But what I'm showing you now is if you want just a change, then you can reset your A. Reset your A to be where you want to start accumulating from, and that'll be your lower limit of integration. Okay. Questions? All right, so we need to talk about why are we using that. So we talked about we are using a different symbol. Here I'm using t. So we said if our current value of x is our independent variable and we're going to accumulate up until x, why can't we just have x's there, right? So why can't we just have x's there? What's the big deal about having to change the symbol? So let's think about what would happen if we didn't. So I've got another function called capital B of t where I went ahead and made it x. Made it all x. So I want to investigate. Let's talk about what at 10 minutes. Let's look at both of these functions at 10 minutes. Let's start with b first. If I were to do b of 10, can you rewrite? So if the value of x is 10, I want you to rewrite this integral expression for an independent value of 10. All right? Now, rewrite this for an independent value of 10. Now, dx means a really small change that has nothing to do with the 10. Okay? But how would you rewrite this for independent variable of 10? It would equal, so here, p of 10 equals what? I've got my rule for b, and now I want the correspondence point for x equals 10. Where's Samuel Bundy? Samuel Bundy, okay. What would it be for x equals 10? Yeah, so we're going to now apply the rule for when the independent variable is equal to 10. Almost. So go for it. Tell me. Okay, the integral from 0 to 10. Yep. 10. So what is that? That's a really small change in x. Does it have to do with 10? No. So it's going to be dx. Okay, so what is that doing? From 0 to 10, r sub t of 10 dx. What is r sub t of 10? What kind of rate of change is that? What's that? It's an exact rate of change. So between 0 and 10, where is this expression going to apply that exact rate of change of RT of 10? Where between 0 and 10? Only at 10? Where is it going to do it? It just at the moment 10. Is that expression the same? It says, what does it say? It says it's the accumulation of all changes of at what rate? Is this a single rate or many rates? Single rate. That's a single rate. So what's going to happen? It's going to accumulate changes as x changes from 0 to 10 at a single, what, constant rate of RT of 10. What is that? We all know. Here's RT of 10. It's the best constant rate I've drawn all day. Okay? But it's not great. So do you see that that b function, that's RT of 10 right there. Right there is RT of 10. So that expression is going to integrate, it's going to accumulate changes at a constant rate of whatever RT of 10 is, starting at 0 and ending at 10. That's what that expression says. You see that? Because that is a single constant rate. Does that give the right accumulation of changes in temperature from 0 to 10? What's the real rate function? The blue one. So is this going to give me a value too high or too low? This accumulation, the accumulation of changes, the b function, is it going to give me an accumulation of changes too high or too low? Way too high. It's not following the rate curve. It's just accumulating at this constant rate of RT of 10. That's what happens if you have x here, because for as the current value of x changes, you're just going to have the constant rate for the whole interval. From 0 all the way to the current value of x, you're going to have a constant rate. So it doesn't work. So what do we need instead? We need a different symbol for t, or a different symbol. It is an x value, but it represents what? Every changing x value from 0 to x. We need that to change to give us the changing rate function. So whatever symbol you use here, whether it's u or v or t, little t, okay, represents what? X changing from a to x, so that we're integrating and accumulating according to the rate function, not according to the constant rate that's the same as the final rate. Okay? That's what putting an x in there would do. You would just end up accumulating at a constant rate equal to the final rate, that black line that I drew. So we need another variable that's also x, but that's going to change from 0, in this case from 0 to 10. We need this value t. It's going to change from 0 to x. And then the rate will change with it. Okay? So let's see the two values. So I want to do a of 10. So the accumulated changes according to the rate function, 2.8. According to just the final rate function, when we do it the right way, we get a change of 2.8. If we do it the wrong way, we get total accumulated changes of 9.3. That's what we predicted. Way too high because it's accumulating at a constant rate the whole way. So that's why these will match. Okay? This is your current value. It's where we're accumulating to. Those match. This must be something different. So I should have done it up here. So those have to match. These have to match and be something different. Match and not be x. And then it works. Because then in this case, t, it changes from 0 to x and gives us the accurate rate of change curve. Rate of change curve for every value of x, okay? Rather than a constant rate that would happen if you use this way. Okay, so let's practice a little bit of that. Any questions on that? Okay, so here's some expressions. Listen up, don't start talking. We're going to determine if it represents a valid accumulation for its rate function. That's what we just talked about. Does the expression, will it validly compute the accumulation according to the rate function? What's intended, right? You want to identify all the parts of the expression by the meanings, and then introduce function notation to rewrite the definition. Let's just do A, B, and D. We don't need to do C because we've talked about accumulating without a function. So we're going to do A, B, and D for each one. Get a partner. Real super important here. Super important. Do A, B, and D for each one of those.
Yeah.
Okay. So when we learned this whole process, right, we used very specific notation. We said R sub f, exact rate of change. Then R, approximate rate. Then A, approximate accumulation. Then A sub f, exact accumulation. So now, that was just to help us learn it. So now we're going to break out of that a little bit. And so when you see an integral, so it's like, okay, g of t. Well, so it's g of t. It's not named r sub something of t. But it's still just a function. So in an integral expression, what kind of function is it? It's an exact rate function. So it was just an aid. That progression of notation, the r sub f, r, a sub f, was just a helpful aid in the process. But now, when you have an integral expression, the function that you'll have will always be, no matter what it's called, it's an exact rate function, right? Like r sub f before, r sub w, or r sub v. Okay? All right, so valid expression? Okay, and so what does it mean? So, someone came up and stole my sheet. Tricky. Did you fall? That was good thinking, you guys. Get the sheet. Where's my pen? All right, I'll just have to remember who I called. Okay, where's Melissa? Melissa Waltz? Yeah. What does that whole thing mean? Can you tell me in the phrase what that whole thing means? And what is the rate of change? What? G of t times dt? G of t. Okay? So this is the accumulation of changes according to a rate of g of t starting from 4 until x. It's the accumulation of changes in our quantity whose rate of change function is g of t starting at 4 until x. Okay, what is this? I put a black box around it. Where is Diana? Okay. Diana, okay. Yeah. Just a black box. It's what? dy. It's like a dy. It's one little amount of change. It's not the sum of the completed intervals. It's not the sum of all the intervals. That, what I put a box around, is one change. It's an m dx. It's an m dx. It's one change. And so what are we doing? We're summing them all up. Makes sense, right? That's what we did in the long a function. We sum up all the little changes. Okay, are any of these invalid? Are any of these invalid trying to be accumulation and it doesn't work? Second one from the top. Oh, does this one, is it valid? Not valid. Why? Because it's going to keep accumulating at constant rates. It's going to accumulate at a constant rate. It says this is not valid. It will give a value, but not what's intended. Not what's intended. Okay? No good. Any others? Bottom right. No good. Okay, so let's do, how about this one? Last one. Where's Eric? Basheklian. Eric? No Eric? Hassan. Kurt. Jeanette Smith. Jeanette. How about this last one that I put a circle around? What does that whole thing mean? Yep. Yeah, the whole expression means what? Can you say what it means? Uh-huh. She said the exact accumulation as we change from 10 to 15 at the rate a times sine e to the a. How'd she do? Right, well done. So it's the accumulation of changes according to that rate function starting at 10, ending at 15. So it's an amount of accumulation or a change in accumulation. Questions on, if you want to talk about one of these two in the middle, I'll stick around here and you can come down and visit.